then it means that this has roots, right? This has solutions. And that means that this quantity can be both positive and negative. This quantity takes positive and negative values. One way to convince yourself is just to, plot AT squared plus BT plus C. You know that there's two roots, so it might look like this, or it might look like that, depending on the sign of A. But in either case, it will take values of both signs. So that means that your function will take values of both signs. W takes both positive and negative values. And so that means we have a saddle point. While the other situation, when b squared minus 4ac is negative, means that this equation, this quadratic, never takes the value 0. So it's always positive or it's always negative, depending on the sign of A. So the other case is if b squared minus 4ac is negative, then that quadratic doesn't have a solution, and it could look like this or like that, depending on whether A is positive or A is negative. So in particular, that means A x over y squared plus b x over y plus c is always positive or always negative, depending on the sign of A. And then that tells us that our function w will be always positive or always negative, and then we'll get a minimum or a maximum. Okay, we'll have a min or a max depending on which situation we're in. Okay, so that's another way to derive the same answer. And now here you see why the discriminant plays a role. That's because it exactly tells you whether this quadratic quantity has always the same sign or whether it can actually cross the value 0 when you have a root of a quadratic. Okay, so hopefully at this stage you're happy with one of the two explanations at least. And now you're willing to believe, I hope, that we have basically a way of deciding what type of critical point we have in the special case of a quadratic function. Okay, so now what do we do with a general function? Well, so in general, we want to look at second derivatives. Okay, so now we are getting to the real stuff. So how many second derivatives do we have? That's maybe the first thing we should figure out. Well, we can take the derivative first with respect to x, and then again with respect to x. Okay? That gives us something we denote by partial square f over partial x squared, or f sub xx. Then there's another one, which is f sub xy, which means you take the derivative with respect to x and then with respect to y. Another thing you can do is do first derivative with respect to y and then with respect to x. That would be f sub yx. Well, good news, these are actually always equal to each other. Okay, so it's a fact that we will admit. It's actually not very hard to check. So these are always the same. We don't need to worry about which one we do. That's one computation that we won't need to do. We can save a bit of effort. And then we have the last one, namely the second partial with respect to y and y, f sub yy. Okay, so we have three of them. So what does the second derivative test say? It says, say that you have a critical point x0, y0 of a function of two variables f, and then let's compute the partial derivatives. So let's call capital A the second derivative with respect to x. Let's call capital B the second derivative with respect to x and y, and C equals f sub yy at this point. Okay, so these are just numbers because we first compute the second derivative and then we plug in the values of x and y at the critical point. So this will just be numbers. And now what we do is we look at the quantity AC minus B squared. I am not forgetting a 4. You will see why very soon. So if AC minus B squared is positive, then there's two subcases. If A is positive, then it's a local minimum. The second case, so still if AC minus B squared is positive, but A is negative, then it's going to be a local maximum. And if AC minus B squared is negative, then it's a saddle point. And finally, if AC minus B squared is 0, then we actually cannot conclude. We don't know whether it's going to be a minimum, a maximum, or a saddle.